The first is that all weak interactions we studied till now, or processes better, are described by Hamiltonian. Maybe I will. Okay. Which has character current times current. Second, all the currents have the same V minus A structure. And the third is, after introduction of mixing, all currents have the same coupling. Between each other. So it's GF after introduction of mixing. Well, actually, precise measurements of 4 fermionic coupling constants in different processes realized that G mu square, this is 4 fermion coupling which appears in the processes with muon, in particular muon decay, equals G beta plus GK. So this is coupling which appears in fine decay and beta decay, and this is what appears in K decays, which actually confirms this possibility to parameterize all these couplings in the following way. So this is what we call G Fermi, and then square this. This is G Fermi cosine, theta Kabiba, and this one G Fermi sine, theta Kabiba. And we need, of course, square them. And we see this parameterization precisely matches observations. Now, this universality can be represented in the following way. We can introduce total current, which includes quark current plus electron current plus muon current, and therefore, and then Hamiltonian can be written as GF square root of 2 G alpha dagger times G alpha. So I see all kind of variety of the processes, and we just discussed few of them, can be described by this simple expression, which is actually a great achievement. So we have 3 terms here and 3 terms here, and so we have 9 different products which describe different processes. Well, actually less, because some are kind of redundant. But before this, let me also write the following diagram. So we have quark current have electron current, and we have muon current. And then the processes can be characterized by products of these currents. So, for instance, this current and this give muon decay. And of course, scattering of electron neutrino or muon neutrino on electron, for instance, also follows from this. Now, this gives us the processes, and also this, like decay. This is like a decay of pion, decay of K mesons. This is beta decay. And you can continue to put in different processes in this diagram. Now we can depict this in a slightly different way. We have current quarks, current of electrons, current of muon and corresponding neutrino, and we multiply this by Q, electron, and muon currents, and then we may have different connections here. Right, all possible connections, and you can find which type of the processes are realized in this way. So we haven't discussed product of quark current onto quark current, and this, for instance, describe the processes of K decay into 2 pions. I mentioned this process, but here you see there is no leptons, and that process is described by the product of 2 quark currents. You will have some exercise also to play with this. Questions? Well, it's important to really understand how the structure appears. Yeah?
All decays are weak interactions caused by weak interactions?
Well, you see, everything is written here. Now, the question is, what is, they have the same coupling constant, which is weak coupling constant. Now, of course, there are strong decays, which are not, which we haven't discussed them. Well, a little bit we discussed them due to strong interactions. So, say, some particles like phi star decays into 2 pions, and this is 10 to the minus 21, 22 seconds decay time. So here decay times are 10 to the minus 6, 10 to the minus 8. For heavier mesons, we will discuss it's 10 to the minus 12. So, and what is characteristic of these decays? As you see, we have here 4 fermion interactions. So in one point, there are 4 fermions. Now, what we have discussed already, that may be the result of exchange of some heavy particle. And this is hidden here in this G Fermi, which is actually dimensionful coupling, and it is 1 over the mass square. And what we will see eventually that this is mass of the W boson, which is staying in the denominator. And so this means that it's a short range interaction. At least all the processes, all the cases which we have discussed till now are due to weak interactions. But we will see also decays due to electromagnetic interactions, like J-psi, what we will discuss next. It decays into plus and minus, and this is due to electromagnetic interactions. And of course, there are plenty of decays due to strong interactions, which are very fast. Well, let me make another comment here. Actually, one still needs to check that everything matches in this simple scheme, and the currents have this V minus A structure. Actually, it took more than 10 years, and people made different checks of this universal theory. What you can actually imagine that the interaction can be organized in different way. For instance, instead of currents, you may have just scalar times scalar, which means that inside this, for instance, neutrino and electron, you will have not V minus A, but just scalar structure. So there is no alpha index here, or pseudo-scalar, or tensor structure. So in general, you can write 4 fermionic interactions in very kind of general form using different structures. Okay, it can be scalar times scalar, or pseudo-scalar times pseudo-scalar. When we have only gamma 5 matrix, not gamma mu and gamma mu, gamma 5, but just gamma 5. Or you may have tensor sigma mu and sigma mu instead of V minus A structure in the current. So what people did, they have written a general expression for 4 fermion interactions, and then put bounds on other structures like scalar or pseudoscalar. Actually, this is an important problem still now, and even now we are continuing to test this V minus A theory, because some deviations may actually testify for existence of right currents when we have V plus A additional structure, and that may testify for wider extension of the standard model, say left-right symmetric models. Or still there's some sense to look for the processes when you have not alpha here, so vector structure, but scalar or pseudoscalar, because we know that there are scalar particles. We know Higgs is discovered. Of course, for Higgs, the coupling is too small, but in principle, it should lead to kind of changes of this of this structure. Corrections are very small. If you go beyond the standard model, then you can easily generate structures which deviate from V minus A. So in this way, we are looking for physics beyond the standard model nowadays. So there are quite stringent bounds though on all these other structures which deviate from V minus A. Okay? So next topic is charm quark. So this is another principle which actually was realized here. And this is quark-lepton symmetry. Charm quark. That was introduced theoretically. And there were 2 motivations to introduce charm quark. So what we have studied till now can be described by the following doublets of fermions, mu E and E, and this doublet means that you have current when you have electron neutrino transformed to electron and vice versa, for time being. So that you will see then deeper sense in this. We also have nu mu and mu, right? That is in muonic, for muonic current. And we have also U quark, and then d theta. Actually, what is more correctly is right du, but it is approximately d theta. Because when we introduce third generation, it will be more mixing angles, and we will have more complicated structure. So that's what we have already discovered till now. Now the question is, and actually it was a question of last lecture, we can have another combination of D and S quark, which is orthogonal to d theta, and it can be written like a cosine theta cabibo S minus sine theta cabibo d quark. So which means that we have some other degrees of freedom which are not participating in interaction. So why? The question is why we have this this combination which doesn't appear, it doesn't act in no way. This is one question. The second one, you see here kind of asymmetry. We have 2 doublets of leptons and only 1 doublet of quarks, and this is kind of just combination which doesn't interact with anything else. Bjorken and Gleshow in 1964 proposed that maybe there is another quark which actually recover quark-lepton symmetry, and they call this charm. And this charm quark probably form doublet with S theta. So this is what is quark-lepton symmetry. Which is realized in full strength in grand unified theories, like actually Gleshow was one of the persons who started grand unification. Okay, so this is hypothesis, and this means that it should be another quark, which actually forms the current with this orthogonal combination S theta, right? So there is a current in processes under which charm can be transformed into S for particles which are in this S theta, and vice versa, particles in S theta, that is S and D, can be transformed into charm quark. So now we have analogy, which is that neutrino electron corresponds to U quark, electron corresponds to D quark, muon neutrino corresponds to charm, and the muon corresponds to S. Now let me put here still theta, or without theta, you can even consider it this way. So we have 4 leptons and we have 4 quarks, which is nice. That's nice. Well, the symmetry is, or universality are very important principles which actually work. And, a number of developments are related to realization of these principles. So this is the first motivation to introduce charm quark. There's another one which actually is related to experimental results. So first is quark-lepton symmetry, and the second is problem of flavor changing neutral currents. In particle physics, you will meet this kind of combination continuously. This is an important issue in particle physics, and we will repeat this again and again. So this is flavor changing neutral currents. So what is this problem and what are these currents? Electrodynamics is based on neutral currents. We have electron and we have electron final state. So we have the current when electron transforms to electron, or muon to muon, U quark to U quark, etc., proton to proton. And this is of course related to neutrality of mediator, which is photon. So we have current, and the current is neutral. So we can treat the current, which is electromagnetic current, is E gamma mu E, at quantum level as operator, right? And the charge of this operator is 0. And it couples with photon. So we also can introduce neutral current for U quark, so being gamma, etc. Now, what we have in weak interactions? In weak interactions, we can also introduce neutral currents. Till now, we discuss only charge currents. So, but we can talk about the currents of the type when D quark go to D quark. Right? And here is some heavy mediator, but something, then say, for instance, we can have here nu and nu. So that will be the process due to neutral currents. But also we may, in principle, introduce transition of d quark to s quark. So the current of this type, that is, we have S gamma mu with some structure and then D. So that would be current responsible for such a transition. This is the example of so-called flavor changing neutral currents. Particles like U, so D, S, that's a U, and then char. So they are referred as quarks with different flavors in general. So we'll introduce even more quarks later. And so we call these states as states with definite flavor. It's a kind of general notion. Flavors, different flavors. And here, of course, with this transition, we have flavor changing, right? So the flavor changes because the type of the quark changes. Right? So we have no such things in the case of electromagnetic interactions because of gauge invariance. Probably we should study. So, for instance, there is no transition of electron to muon. In principle, this is also neutral current, right? But there is no such a transition because of gauge invariance. Now, here the question is this current exist or not? How we can test this? And the very good test is decay of K0 into mu plus and mu minus. Remember, K0 from the quark point of view consists of S anti-quark and D quark. Right? So this is K0. This is its composition. S anti-quark and D quark. And if such a current exists, then these two guys can annihilate, like in pi decay, right? And then produce this mu plus and mu minus. Experimentally, such a process is extremely strongly suppressed. So eventually people have discovered the decay of K0 into mu plus and mu minus, but it is very strongly suppressed. So branching ratio for this process, which is rate of decay into mu plus, mu minus, over total rate is 6.8, maybe now it's more even precise, 10 to the minus 9. 10 to the minus 9. It's not 1. Which means that even if we introduce such a neutral currents, the corresponding coupling should be extremely strongly suppressed. Extremely strongly suppressed. So one can introduce some 4 fermion coupling, which is responsible for such interactions. However, the corresponding G should be, say, 5 orders of magnitude smaller than G10. So when we square this, we get this 10 to the minus, or 4 orders of magnitude smaller. Then we get this small quantity. Well, we can say that maybe theory is organized in such a way that there is no such a current. So if it's so small, maybe it's just 0. Coupling is 0, so there is no such a coupling. Now the problem is that even if you do not introduce this type of the currents, you will still have transitions which will lead to this flavor change. Even using only charge currents. So even using the elements which we have already introduced and discovered. So let me show how this decay may occur without fundamental or elementary neutral currents. So this process may occur at one loop level in the following way. So have you started to study Feynman diagrams? No. I see. I can give you to compute this. Then you will learn how to do this. So the process is the following. S bar Let me write this in this way. Nice, we can write this in different ways. So D quark can transform into U quark, right? We know this, such a current exists. Now, U quark can transform to S quark. This also exists. So that goes with cosine theta Kabibo, and then go to with sine theta Kabibo. All the sine is smaller than 1, but still such a transition exists, right? Okay. Now, we can close this diagram in the following way. So this is mu minus, this is muon neutrino, and so this is mu plus. So this transition exists. Oh, so let me, wait, that's that way, yeah, so that's emission of mu plus, the R is here. Both these currents exist. This is the current of muon neutrino and muon. And so we have also these couplings, right? Because, let me see. So, so all these kind of the couplings exist, right? So you have this product of two currents. This is muonic current and this is U current. And actually we used this, for instance, process. It was measured when we discussed difference of muon neutrino and electron neutrino. We studied scattering of muon neutrinos with emission mu minus. And this is precisely this vertex which is responsible for such a process. So it's not only, we use the same currents, but even we have discovered these 4 fermionic interactions. So actually this one we discovered in K decays. So K decays, some of these K decays are due to this vertex. So once we introduced our Hamiltonian, in quantum field theory it's unavoidable to compute high order corrections or the processes due to high orders in the interactions. So if you want to be consistent, you must take into account this process. And this process leads to precisely decay of K0, this is K0, this is time, K0 into mu plus mu minus. Okay? Questions?
Is this the same process that we draw there, like very zoomed, or is this one?
Well, if you want, yeah. So that's actually what is here. It's zoomed, so there is no elementary. I have written this as elementary current. But suppose we do not introduce elementary current. But then that will be produced in this way in the second order process. So instead of just what we had before, which is point-like interaction of 4 fermions. So we have no point-like interaction. This is not point-like interaction. Right? So this is kind of effective interaction, which produces for us the decay.
When we try to calculate this using quantum field theory, we need to consider this bundle of order correction.
No. So yeah, but we say, okay, suppose we do not introduce even such a coupling in our fundamental theory. Suppose there is no coupling. And then actually in the standard model there is no such a coupling. But then we know that charge current exists. And just using known charge currents we can construct this type of the process, which again leads to K0 to mu plus mu minus decay. Now let us try to compute this diagram. Also you don't know how to compute, but nevertheless it's big fun, right, to do something which you don't understand and don't know how to do. Well, so, but what I will show is quite strict. It's not a joke. So how you would compute this amplitude? You see we have 2 4 fermionic couplings, and therefore the amplitude should be proportional to G Fermi squared. Okay? Now, we have sine here and cosine here. So now diagram will be proportional to sine theta multiplied by cosine theta Kabibo. So let me put here proportionality, because I will not follow all the factors, numerical factors. then it will be integral. Once you have loops, you need to introduce some for momentum here, which is running in the loop. So the problem that this Q is not fixed by external momentum. You can still satisfy energy and momentum conservation for whole the diagram. However, momentum which is running here is not fixed, right? So which means that you need to make integration over all possible values of this for momentum. Actually, it's for momentum. It's not really for momentum. It's not just momentum. So once you meet this type of the diagrams, loops, you need to make integration, and you will study this over momentum. But physics is clear. So you produce this particle, and then produce these particles, and these particles can be can have any momentum. The only important thing is that you need to satisfy energy and momentum conservation for external particles. Well, you also satisfy here, but you can satisfy energy and momentum conservation in these vertices also, because you have big Q here, but big Q is going out. So you can satisfy, and everything is okay. So you need to make integration over Q. And that gives you the integral of the following type. All four components, 2 pi and the 4. And then I need to write all the factors which appear in this diagram. And what appears here is the vertex, which is gamma mu 1 minus gamma 5. That's what comes in from the vertex. Then it will be a propagator of u quark, and so I'm moving from this vertex, so in this direction. Then I need to write propagator of u quark. Have you studied propagators? Well, at least propagators, no? Or green functions. Okay, so green function. So, which is q for momentum of u quark minus mu, and actually this is for momentum multiplied by gamma matrices. That's what appears here. And in the denominator you will have q u square minus mu square. So then you are arriving in this vertex, and you need to write what is in this vertex, and you will get here gamma mu 1 minus gamma 5. And then you need to write propagator of green function of neutrino. And neglecting the mass, I can write this in this way. It's q squared neutrino.
It's just this way. Okay.
Now, usually you need to make integration in principle up to infinity, right? So this, and then you meet this problem with infrared divergences in most of the cases. And in fact, this diagram is divergent. So you need to make computation of this integral. So in the first approximation, I will make some estimation. I can say that momentum of u quark is approximate momentum of neutrino, neglecting momentum of external particles. So usually you are doing integration, then you need to take into account also these particles which are appearing here. But then you need to make integration over q up to infinity, so you can neglect this difference. So this integral has the following structure. So you have this dq to the 4, and then from this propagator it's q over q squared, and then from this is again q over q squared. And so what you have here, so you see, you will have integral dq to the 4th over q squared. So this integral is divergent, right? So you integrate up to infinity, and it diverges as so upper limit, if I introduce upper limit, as lambda to the 4. So let me introduce here lambda, and then I need to put lambda go to infinity in principle, right? So that is lambda to the square, sorry. That's lambda to the square. So the integral is divergent. So one way to make estimation really to introduce this cutoff. So they are saying here introducing cutoff of the integration. And if you introduce this, then the amplitude will be proportional to G Fermi square multiplied by S theta, let me write cosine theta, and lambda square. Now what is this cutoff? Again, I'm kind of giving you elements of quantum field theory also. That's beyond my course. But anyway, in principle, if you have constructed consistent theory, this consistent theory should somehow reproduce kind of cutoff. Usually it is because you introduce some new particles to make the theory consistent. And then this lambda is the mass of some new particle. Lambda is of the order of mass of some new particle. Right? Now, what we can do, estimating this diagram, we can say, okay, since we haven't seen any new particle which could help us, at least this was by that time, eventually we discovered W bosons, and so then it was essentially the mass of the W boson square, or electroweak scale. But at least we need to take lambda, which is bigger than masses of all known by that time particles. Right? You understand logic? Because if you take lambda, which is smaller than already reached, say, energy at accelerator, then we should see something new, some new particles which lead to then to cutoff of the integrals. Since we haven't seen anything, then we can say that this lambda should be at least bigger than, so the heaviest particle we discovered by that time, and by that time people discuss particles in GeV range. So one is to take lambda bigger or equal, say, 1 GeV. So that would be a reasonable cutoff. But even if we take the minimal possible scale, 1 GeV, then this estimation would lead to much bigger decay rate than it was observed. Okay? So even for 1 GeV, and I don't want to do this explicitly to make all this, because I need them to put some factors. But you can check that for 1 GeV you get this branching ratio, I don't remember precisely, something like 10 to the minus, I think 10 to the minus 4 instead of 10 to the minus 8. Still you have far way to go. And you need to have some other suppression. Okay? You understand the problem? Questions? Now, how you would try to solve this problem? So what I'm saying that even introducing cutoff doesn't help. Even if suppose you have introduced W boson, even worse, because if you put here mass of the W boson square, which is around 100 GeVs, then you would have, you know, huge result. Then you would have branching ratio 1, or maybe 0.1, something like this. So any idea how to solve the problem? So which means that we need to invent some other mechanism, additional mechanism, to suppress this type of the diagrams. And this was kind of the move what Glesio, Mayani, and Iliopoulos did. So what they suggested is the following. I actually think, I remember this trick. It might be useful for your studies in future. So they were saying, maybe there's some other particle here which produce diagram of similar type which leads to cancellation. So diagram but opposite sign, and then we have cancellation. And so precisely, and probably it's not accidental because Glesio has introduced charm quark, their suggestion, which is called G mechanism, which is let's show. So let me add Miami. And you can see Miami around because he is he is still, I think, the chairman of ICTP Scientific Council and Steering Committee. So what they suggested in 1970 is the following: that we have this U quark and the d theta, but let us introduce this charm quark and S theta. That was suggestion by Gleshow and Bjorken before, to just from the point of view of symmetry between quarks and leptons. Okay? Then what will happen? Due to this additional doublet and therefore currents, you will have similar diagram, but with charm here, right? You will have charm here. And for charm, you would have here transition of d quark to charm, and this is determined by this orthogonal combination. Remember, this is sine theta s quark, cosine theta s quark minus sine theta d quark. And what is important in the orthogonal combination, there is minus sign. And therefore, for this transition, and this will be determined by this S part interacting with charm, you will have minus sine theta, and here you will have cosine theta. So let me put this in the circles, what you would have for another diagram but with U quark, so it's with charm quark. So you will have precisely the same diagram, but with charm quark instead of U quark, and you need to substitute these coupling constants in the vertices. Okay? So then you will have total amplitude, which is amplitude due to U plus amplitude due to charm. And these two amplitudes will have different signs, right? Because of this precisely minus sign, and this minus sign will propagate to the sign of the amplitude. So the amplitude will be proportional by the product of this one and that one for charm quark. So you can actually write explicitly this amplitude for charm quark, but let me just take the part. You need to sum up these two amplitudes, but what you will get under integral, instead of 1 over q squared minus mu, so you had such an element. After introduction of charm, and therefore integral with charm quark, you would have 1 q squared minus mu squared minus 1 q squared minus m charm squared. So including charm would lead and can be accounted by substitution and expression for the amplitude, which I have discussed already before, the propagator by of u quark square, to this expression. So this is what comes from a diagram with charm, and the only difference is this minus sign, which comes from vertices, and mass of charm quark, which differs from mass of u quark. If the mass of charm quark would be equal to the mass of u quark, you would have complete constellation. You would get 0. So then the only difference, a non-zero value of this amplitude, appears because of difference of the masses of charm quark and U quark. So that can be, this expression can be written as mc square minus mu square, and then these two propagators, and that can be written as delta m square over q to the fourth power, if I neglect these masses here in denominator. And delta m square is mass of charm quark minus mass of the U quark. So tell me if it's clear, otherwise I will add some more details. So what is staying here is delta m square over q to the fourth approximately. Okay, just combine these two propagators. So now my integral becomes logarithmically divergent and not quadratically as it was before. So we have delta m square and an integral d q to the fourth and then q square over q to the sixth. So that will be eventually integral d fourth q over q to the fourth power. So that comes from nominators which I have omitted here. So it will be q here for and then q square because another q will come from neutrino. Okay. So this is logarithmically divergent. So that's fine. Then you can make your cutoff where in a reasonable, say, place, and that of course produce some uncertainty, but still it's okay. But what is important that we have these factors in branching ratio, which is proportional to the rate of this decay, and which will be proportional to sine theta Kabiba square, because I have written expressions for the amplitudes before, and now I should square, multiplied by cosine theta square. And here I need to put here delta m square over lambda to the lambda to square. And lambda is cutoff. And that should be squared. So because that appears in the amplitude and then in the probability it should be squared. So this is additional factor which appears in the rate. Again, I'm not going to put here proportionality sign, which actually produces enough suppression if delta m square is say 1 GeV square of this order, and lambda square is 100 GeVs squared. So in this way, and also taking into account some of these factors, I will get 4 or 5 orders of magnitude additional suppression. And that will fix the problem. So then I will explain the observable value of this decay rate of K0 into mu plus mu minus. So this factor called gene factor. So which actually appears in various other places, especially when you deal with flavor changing neutral current processes. This is gene factor. That actually allowed also to make estimation of the mass of the charm quark. That time already standard model has been introduced, and the scale around 100 GeVs, which is the scale of mass of the W boson, was already known, and that allowed to put the bound on the mass of the charm quark. And the mass of the charm quark should be smaller than 1 to 2 GeVs. To explain the rate of K0 into mu plus mu minus. So that the bound has been obtained from rate from gamma of K0 into mu plus mu minus. Questions?
The idea of having this cutoff, which is proportional to the mass of a boson of a mediator, it means that in the diagram we have, instead of the loop, we have just one boson going from one branch
So
to the other.
instead of say this, you would get box diagram of this type. This W. This is how this diagram looks like. And of course you will have to boson propagator and the diagram becomes convergent. Okay? And you will get this lambda, which is the mass of the W boson. This is what is running here. You have two propagators, which is 1 over the mass of the W boson. And of course, at very high Q square, you will have another Q to the 4th power, which comes from these propagators. Okay? Then the diagram becomes convergent. More questions? Okay. So before I will discuss discovery of particles which contain charm quarks, let me discuss a little bit some kinematical issues which are important in all these discoveries. So this is what is used practically in everything what was in this epoch of accelerator discoveries and now even. So this is what we are doing these days also. So elements of kinematics. We have introduced already the centrum of mass system, which is defined for the system of particles as the system where the sum of momenta of particles is 0. So let's take some initial state and some number of particles, and then we can define the centrum of mass system, the system in which momentum, total momentum of particles in a given state is 0. We also introduce the total energy in the centrum of mass. In the centrum of mass system as square root of S, and S is Lorentz invariant, which is sum over I pi square, which is the sum over energies squared minus sum of momenta squared. And if you are in the centrum of mass, then this is 0. And what you will get, the square root of S, is just square root of the first term, which is the sum over I energies of the particles. So this is the origin of the name of this invariant. This is total energy in the centrum of mass of the system of particles. Okay? Good. So now let us consider the following process. Suppose we have some number of particles which annihilate in a single particle x. So we have some particles in the initial state, and in the final state we have a single particle x. So example is, and we will discuss this, E plus, E minus annihilation in some unit particle. Okay. So let us apply energy and momentum conservation to this process. And so what we will have is the conservation of momentum tells us that the sum over momenta is the momentum of this produced particle, and the sum of the energies in initial state should be equal to energy of particle x. Right? So this is energy momentum conservation. Now let's go to the centrum of mass system. And in the centrum of mass system, sum of Pi equals 0, right? This is our definition. And therefore, Px should be 0, right? According to the conservation of momentum, which follows from the first equality. This means that the particle in this system, produced particle, is at rest. And therefore, the second equation becomes sum over the energies is equal to the mass of the particle. And this is nothing but our square root of s. Which means that square root of s for such a process equals mass of the particle. So if you have the process in which some number of particles annihilate in a single particle, then the mass of this particle equals total energy in the center of mass. And this is invariant, Lorentz invariant. You can measure it in any system. So once you know that you have process with production of single particle in final state, then square root of s of the particles in initial state give you the mass. So this is the way how to measure the mass. You observe the process, you see that you produce a single particle in final state, and then you can find what is square root of s, and then you find what is the mass of the particle. So this is the way to measure the mass of the particle. Okay? So let us introduce another notion. The notion of invariant mass of the system of the particles. So suppose we have some initial state which produce a number of particles A1, AN. So now we consider inverted situation, so we are now considering the final state particles. We can define the following invariant, W square, which is sum over 4 momenta of particles in final state, from 1 to n, squared. Which again can be written as the sum of energies squared minus sum of momenta squared. So now let us consider these final particles in the centrum of mass system of this particle. In the centrum of mass of these particles, the sum over momenta is 0, and our W square, or okay, let me put W square, is just equals sum of the energies square, and W itself is the sum of energies of particles in the centrum of mass frame. Okay? So, now suppose we have a single particle. Question?
There is no cross-terms in that product, right? Or do they?
Between this and that?
Uh-huh.
No. That's how you construct the square.
Between different momentum, you have different particles, I and J products.
No, I'm defining this in which sense. Yes, of course you will have, but if this, if you open this square, but if this is 0, then why should worry about this interference? Okay?
No, I mean for the first 4 vectors square.
For this?
Uh-huh.
No, this is for, in a relativistic quantum theory, you will have this expression, right? So you have some 4 vector. So if you have 4 vector square, then it will be energy square minus momentum square.
So for one.
Oh, for single, for system, it doesn't matter. So this is how we define these 4 vectors. For 4 vectors, there is no interference of what? You want to have interference of this and that?
Yes. No. Interference between P3 and P4, for example. Because they are additive and then
yeah, if you open this, of course you will have interference between this and between that, but I don't worry about this. For my goals, this is not needed, for this consideration. So let me consider the process when I have a single particle in initial state, which then decays into this A1, An, and a number of particles in the final state. And again, let me apply energy and momentum conservation. And what I will write is Ex equals sum of E and Px equals sum over Pi. Okay? Now in the centrum of mass system, I will have the sum over Pi equals 0. And therefore, from this equation, I get that Px is also 0 from expression for momentum conservation. Therefore, in the centrum of mass system, particle X should be at rest. And therefore, the first equation becomes mx equals sum over energies, and this is our W. Well, simple consideration. If you can repeat again, but surprisingly sometimes that produces problems for solving some tasks. Okay, so what does it mean for such a process when we have single particle in initial state and some system of particles in a final state? The mass of particle mx equals invariant mass of particles in final state. So actually, this is the origin of the name of this particle, of this quantity, W. So the mass is given by invariant mass of the particles in final state. So that is, if you see some process and you know that these particles in final state originate from decay of a single particle, then what you do in any reference frame, because W is Lorentz invariant, you just reconstruct this W, and that will give for you the mass of particle. So this is the way how to measure particle which decays into system of the particles. Usual situation is like this. You have interaction, say, of some particles in initial state. Then you have a number of particles in final state. And among these particles, you may consider subsystem. So, and you may suspect that these particles, among other particles in final state, originate from decay a single particle. So that the process actually is, you have some number of final particles, then production of single particle here, which then decay, for instance, into two particles. So why you can be suspicious that something originates from a single particle decay? Suppose you have interactions of hadrons. And suddenly you see here E plus E minus, or mu plus mu minus. So here you have some hadrons, here you have some hadrons, and then you see this appearance. So you may suspect that maybe this E plus E minus appears from decay of a single particle. It may happen so, or may not, but you can try it. And you can see, if you observe many events of this type, for each event, you can reconstruct invariant mass. And imagine you observe that in all these events, invariant mass is the same. Then that would be actually indication that you have these particles originating from decay a single particle. And this is how many discoveries have been done. Okay? So questions? So now I will discuss experiments where charm particles have been discovered.
The gene mechanism is the first and only process that we encounter and try to find the charm.
So the charm, we are not producing charm. Charm is inside, so charm is in the loop. We are not.
Yeah, but I mean, it's the only first diagram or the process that involves the charm work.
In a sense, yes. I don't know if there were some other processes where charm was taken into account as a virtual particle. It was not discovered as a real particle by that time, of course. And I don't think that we have even. I think this is the first process really where people discussed the charm. Or any new type of the quarks. So charm, something else. So, discovery of charm particles. That is particles which contain charm quark. So there were two experiments running simultaneously and announcing simultaneously discovery of this charm, and both leaders got a Nobel Prize for this. This is an extremely important discovery. Again, I'm missing many different discoveries and very important measurements. There were hundreds and hundreds of different discoveries of different particles. Of course, I have no time to expose them. There is no sense. Some discoveries were really extremely important, and especially in establishing of the standard model. So that was one of these discoveries. So one experiment was in Brookhaven National Laboratory in US. And the leader of the experiment was Ting, S-C Ting. And that was in 1974. What he has studied is interactions of protons with beryllium target, and among other interactions in other process, final states, he observed events of the following type: E plus, E minus, and then the rest. This is precisely the diagram which I have shown, of process I have shown just a few minutes ago. So these are the system of hadrons. So this is fixed target experiment. Protons were accelerated up to quite big energy. By that time it's 28.5 GeVs. So hit the beryllium target. And then what they saw is some number of hadrons and then E plus and E minus. So that was the observation. And then he became suspicious that maybe these E plus and minus are produced by, from decay of unique particles. So he tried to test this. How to do this? You need to compute for each event, and he observed a number of events. Then for each event, invariant mass of the pair E plus E minus has been measured, reconstructed. So for this you need to measure momenta and energies of electron and positron. So once you measure this, you can reconstruct this Lorentz invariant W. Okay? So let me write this explicitly, but I will not do many times because we will discuss differently. So you need to measure energy of positron, sum with energy of electron, square, minus P positron plus P electron square, and then take square root of 2. So for each event, you need to measure energy of positron, energy of electron, momentum of positron, momentum of electron, compute this invariant mass squared, and then take square root of 2. So you get this W. Now to measure all this, let me just maybe draw very schematically the experiment. It was this proton beam. And then apparatus was quite more complicated than before, so he used so-called two-arm spectrometer. So you have the target, then the system of magnets, which separate electron and positrons, so electrons are moving in one direction, positrons in another direction. And along these trajectories of electron and positron, there were a set of detectors. You see, the things are more complicated because you need to identify particle. You need to still be sure that this is electron or positron and not something like not like a pi plus or something else. So you need to establish the nature of particle. So he used that kind of symmetric. 3 types of the detectors. And first it was a Cherenkov detector on both sides. Then it was multi-wire chamber. And then it was electromagnetic colorimeter. which are layers of scintillators. So this you need to really establish the nature of particle, measure the energy. By the way, this is what we have discussed. This is what Sharpak was invented and got Nobel Prize for this. These are chambers with wires in different directions, so you can find the trajectory of the particle. So you need to identify that this is electron or positron. You need to distinguish the charge, and you need to measure the energy, and you need to measure the momentum. So what is the result of the experiment? What he did is to construct dependence of number of events on this VEE. And this number of events, this distribution, has the following form. Which consists of background, and these are events in which a plus and minus are produced electromagnetically. So there is a gamma and then a plus and minus. And that has typical dependence with increase of number of events to smaller W, and this is just reflects the propagator of photon. It's like 1/q squared, and therefore that actually leads to the background, which increases to smaller W. Okay? But on the top of background, he observed the peak. And the peak was at invariant mass 3.1 GeV. So this is the first. The second one is he measured, of course, the width of this peak, and the width of this peak on the half of the head was quite narrow, and it was in agreement with just energy reconstruction. So, of course, he measured the energy of this electron and positron and momenta with some accuracy, right? And therefore, for a given event, you measure W, and this W has, of course, error bar, right? So it's not, you don't know precisely, it doesn't precisely coincide. And so you can estimate what is the precision of reconstruction of energy, of W. And it happens that the width of this peak is the same essentially as this accuracy of reconstruction of WEP. So this is accuracy of the experiment, which means the true peak is narrower. So which means that if it is resonance, then the width of this resonance is even smaller than energy reconstruction accuracy or accuracy of the experiment. So narrow, it should be narrow. So now let me ask you the question. Do you know why appearance of new particle should show up as some peak? So what he saw increase of number of events in certain range of this W. Who knows this? Why it should appear as a peak?
Well, I think this is the same reason why they call it resonance.
Okay, so what is the origin of resonance then?
It's constructed way of, I would say interference, but I wouldn't say it for this.
No. So I will have lecture describing this, why it happens so, and that actually the origin is propagator again. So, but I will discuss this later. But just for time being, because I will describe various discoveries if you have production of new particles, it show up as some peak, some excess events in a certain range, and this in the range where you have this W coincides with mass. So what is the conclusion? The conclusion is that here we have this excess of events. We deal here with production of new particle, and which has mass equal to this W in this point, and which is 3.1 GeV. So this is important conclusion here. So that tells us that we have produced new particle with a mass equals WeV. That is determined by position of the resonance. And so interpretation is that you have production of this new particle, which then decay into E plus and E minus. So the mass is 3.1 GeV. So this is decay channel. And the gamma of this new particle, let me put it immediately. This particle was called J psi. So I can put here that X is what we finally call J psi particle. And the rate is much smaller than the observed width of the resonance. So the width of the resonance is much smaller than observed, which is not always. Sometimes we can even measure this resonance curve. So gamma is actually is this width. Well, unfortunately, I need to stop here because that's another experiment at SLAC, which also observed J psi, but then I will discuss this tomorrow. Questions?
When we measure this invariant mass, it doesn't mean that this X particle decays at rest. It decays.
Yeah, this is the power of this Lorentz invariance. You know, this is invariant,
Yeah.
and of course it was moving. So it was produced moving, but you measure mass by measuring invariant mass of the system. Final state. Yeah. Yeah, it was moving actually quite fast because you hit proton with energy 29 GeV is the target, and yes, maybe 10 GeVs energy in some events. Nice thing that measuring this invariant mass, you really probe the mass of the particle and should not worry if it is moving or not.
This X particle also decay in muons?
Yes, later it was also found that it decays in muons, and there are other channels, of course. But that was discovered using this channel. I will tell you more about properties next time. Well, actually, okay, no, I don't want to. More questions? Okay, so next, tomorrow we will continue with slug discovery by Burt Richter and his group. No, it works, right? you switched off. Thank you. Sorry.